Thank you, Dr. Hanif and Dr. Alam. Sorry, I did not introduce you briefly before the presentation, so here it goes. So Dr. Saramad Hanif is a power system engineer working primarily focusing on electricity distribution system at PNNL. And Dr. Alam is a project manager and a senior power system engineer at PNNL. Sorry, guys, I'm really sorry. So now our next presenter is Dr. Thomas Morstyn. He's a lecturer in power electronics and smart grids with the School of Engineering at the University of Edinburgh. And he will talk about managing distribution network constraint and uncertainty within peer-to-peer energy trading platforms. So Thomas, it's good to see you for the first time. So yeah, the microphone is yours.
Yeah, good to see you as well. I'll just get my screen share.
Just a minute, I just stopped sharing my screen.
All right, so is that working?
We can see, yeah, we can see the screen. Yeah.
Okay, great. So hello everyone, my name is Thomas Morstyn. I'm a lecturer working with the School of Engineering at the University of Edinburgh. Thanks very much to UN and Waze and everyone else for helping to organize the session. Today, I wanted to talk about some work that we've done looking at managing distribution network constraints and uncertainty within peer-to-peer trading platforms. And this is work that I also did with Professor Alexander Teitelbaum, Professor Cameron Hepburn, and Professor Malcolm McCulloch when I was at the University of Oxford. All right, so a quick overview of the presentation. First, I'll discuss why do we need local energy markets. Then I'll discuss some different local energy market architectures. And finally, I'll discuss our proposed design, which is looking at integrating peer-to-peer energy trading with probabilistic distribution locational marginal pricing. So why do we want to do localized coordination of distributed energy resources? The idea is that power systems are undergoing a fundamental transition due to the rapid adoption of distributed resources. These are things like small and medium scale renewables, home batteries, electric vehicles, and heat pumps. And coordinating these resources to match local renewable generation with flexible demand has the potential to create value in a couple of different ways. So first, by reducing the net import and export of power in a local network, this will reduce upstream power flows and losses. It can also help alleviate the need for renewable curtailment, which would otherwise be required due to distribution network constraints. And then finally, if we can do this on a very reliable basis, there's the potential to defer or avoid the need for costly generation, transmission, and distribution network infrastructure upgrades. There's also a number of more advanced value streams that could be unlocked by coordination. So these are things like the ability to maintain security of supply by operating a local distribution network as an autonomous microgrid if it's islanded, or operating distributed resources as a virtual power plant to provide flexibility upstream. So the next obvious question is, why do we need market-based mechanisms for local coordination? The idea is that these distributed resources are owned by individual prosumers or proactive consumers who may also have energy management systems and smart meters that could allow them to actively manage their production, consumption, and storage of energy. The challenge is that these prosumers are too small to be incorporated directly into our existing wholesale electricity markets. And at the moment, they operate under traditional retail supply contracts, which individually meter their energy use. And so this provides them with an incentive to individually optimize their resources behind their own meter, but not to contribute flexibility to the operation of the overall system. So a range of different local energy market architectures have been proposed. Broadly, one way of kind of categorizing these is into central dispatch, distributed dispatch, unidirectional pricing, and bilateral peer-to-peer trading. So centralized dispatch basically replicates what we have at the wholesale market level at the local level. And the idea is that a distribution system operator, or DSO, could gather all the information about prosumer resources and come up with an optimal schedule for them. And then the Joule price variables associated with the optimization can be considered to be distribution locational prices, which price energy at the marginal cost of supplying it to particular nodes of the network. Now, central dispatch has challenges in terms of scalability and data privacy. And so therefore, people have been interested in distributed dispatch solutions, which would use distributed optimization algorithms to solve the central problem. And distributed optimization algorithms have advantages, particularly in terms of scalability. The main challenge is that although they resemble market mechanisms with a kind of iterative negotiation procedure, to achieve convergence, prosumers need to augment their objective functions with penalty terms rather than making utility maximizing decisions at each iteration step, which means that prosumers need to be willing to cooperate with the network in some sense. And so the mechanisms can't be considered fully competitive. Now, unidirectional pricing is another approach, which is the idea that if the distribution system operator had accurate forecasts and information about the prosumers, they could come up with a set of distribution locational marginal prices and send these in a single direction to the prosumers. And in theory, these prices would be compatible with the centrally optimal solution. And the mechanism would be scalable since it only involves one-way communication. But there are two main challenges with unidirectional pricing. One of them is that it requires fully accurate forecasts. And then the other is the challenge of Joule degeneracy. And this is the idea that if the central problem has multiple optimal solutions, then although the prices that are sent will be compatible with optimality, you can't actually guarantee that the solution provided by the prices will be optimal or feasible. And so a simple example of this is when you have two storage systems at a single node, and you want them to charge over 2 time periods, but you'd like them to charge at different time intervals due to a capacity constraint. The challenge is that if you send prices unidirectionally to the storage systems, they may both decide to charge in the same time interval and overload the capacity constraint, even though there was a feasible solution, which would also be compatible with the prices where they charged at different time intervals. So bilateral peer-to-peer energy trading is another design, which is partially what we're here to discuss. And it's been gaining more interest generally recently. And this is the idea that rather than being coordinated by a central entity, prosumers could directly negotiate transactions with one another with advantages in terms of scalability as well as prosumer autonomy. So in other words, the ability of prosumers to make utility maximizing decisions based on their own preferences and resource characteristics. The main challenge with peer-to-peer trading is that it's difficult to manage network constraints with bilateral negotiation because the constraints depend on the power injections of all of the prosumers in the network. And also it can be difficult to manage uncertainty because although each prosumer could individually mitigate their own uncertainty, this would lead to a very conservative solution. Whereas from a system perspective, a significant amount of uncertainty is aggregated away when you're looking at the distribution network as a whole. So our proposed design is to combine unidirectional locational marginal pricing with local bilateral peer-to-peer trading with the aim of capturing benefits of each of these approaches. So the idea is that first we have a DSO who would run a probabilistic day-ahead dispatch problem to characterize the uncertainty associated with distribution locational marginal prices, treating them as random variables with some amount of uncertainty. And then based on this uncertainty, the DSO would come up with conservative import and export prices. So there's a spread between the price of buying energy and selling energy at each node in the network. These can be sent unidirectionally to the prosumers and incentivize conservative self-consumption so that the network constraints are not violated. But on its own, this would lead to an overly conservative utilization of energy resources. So to address this, the idea is that by allowing local peer-to-peer trading between the prosumers, additional mutually beneficial transactions can be arranged. And if the DSO is able to properly set peer-to-peer transaction fees, this can help steer peer-to-peer trading away from reintroducing constraint violations. So the first step of this is setting up the DSO probabilistic dispatch problem. The idea is that we want to minimize the net upstream energy costs and battery degradation costs of the prosumers. And the constraints include things like the prosumer battery operational limits, PV generation curtailment limits, and we use a linearized multi-phase power flow model to introduce power flow and voltage constraints. And then we have a number of different random variables in our problem. We have the upstream energy prices, the prosumer load profiles, and the PV generation profiles, which are all uncertain from a day-ahead perspective. Now, for a particular realization of the random variables, though, the DSO can solve the optimization problem as a deterministic one and obtain a set of distribution locational marginal prices, or DLMPs, over the time horizon of the problem. So we want the DSO to be able to characterize the uncertainty of the DLMPs. And to do this, we use a point estimate method where the DSO solves 2n+1 realizations of the optimization problem, where n is the number of random variables. And this allows it to characterize the mean and standard deviations of the random DLMPs, as well as the differential DLMPs, which are the differences between the prices at each pair of nodes in the network. And this could also be done using methods such as Monte Carlo. The advantages of the point estimate method is that although they only characterize the kind of first and second order moments, we only have to solve a small number relatively of problems, and it still accounts for correlations between the random variables and can be applied to general nonlinear model functions. So in this case, we've applied it to linear multi-phase optimal power flow, but you could in principle apply it to any nonlinear power flow method. Okay, so now that we have the DLMP mean and standard deviation values, we can come up with our conservative DSO pricing strategy. And the idea is that day ahead, the DSO will set import and export prices for each node. And at each node, the import price will be the mean DLMP plus the standard deviation multiplied by a value alpha, which we call the price spread scale factor. And then the export price will be the mean minus the standard deviation times the price spread scale factor. And the price spread scale factor sets the level of conservatism where higher values will incentivize greater levels of self-consumption and help manage network constraints, despite any error in the forecast used to calculate the DLMPs by the DSO. And we also then can calculate conservative peer-to-peer transaction fees based on the differential DLMPs and the price spread scale factor. So once we have this conservative pricing strategy for the DSO, we can then also set up local peer-to-peer energy trading with bilateral contracts. And the idea is that within local peer-to-peer platforms, we allow prosumers to negotiate over multiple bilateral energy contracts, each specifying a price for delivering a unit of energy between two prosumers during a particular time interval of a trading horizon. And we have an iterative peer-to-peer market mechanism where at each step of negotiation, agents make utility maximizing decisions in parallel to select their favorite set of contracts to buy and sell. And then contracts that are over demanded, meaning that they're demanded by the buyer but not the seller, have their prices increased. And this continues iteratively until all of the contracts have either been mutually accepted or mutually rejected by both the buyer and seller. And we set up peer-to-peer trading for both day ahead as well as intraday, with agents making decisions accounting for the import and export prices set by the DSO, as well as the peer-to-peer transaction fees. So the peer-to-peer negotiation algorithm is set up with day-ahead trading, allowing the agents to schedule their storage system over the full trading horizon, where they can negotiate trades based on their forecasts of their load and renewable generation. And in addition, there's intraday peer-to-peer trading, where at each time interval, prosumers can trade based on updated forecasts, as well as their obligations from the day-ahead market. And because we have bilateral trading over discrete contracts, we can guarantee convergence over finite time, and the mechanism allows for a trade-off between contract granularity and negotiation time. So if we have more granular contracts, meaning that contracts either have either a shorter in duration, smaller in terms of their energy unit, or have a smaller minimum price increment, then we'll have slower negotiation, but more opportunities for mutually beneficial peer-to-peer transactions. Whereas if we need faster convergence, we can make the contracts less granular, but we may miss opportunities for valuable trades. And negotiation proceeds based on a modified version of the Gale-Shapley deferred acceptance algorithm. All right, so to finish off, we can look at a case study where we use the IEEE European Low Voltage Test Feeder. We had 57 prosumers. These were divided between two peer-to-peer trading platforms, with prosumers only able to trade with other prosumers within their own platform. And this was just to demonstrate that this method allows you to have segmented trading platforms. We have 15 prosumers that only have single-phase inflexible loads. We have another 40 prosumers that also have PV sources and home battery systems. And then we have two larger community-scale PV generators. And we assume that these larger generators, the DSO, can curtail during operation if necessary to prevent constraint violations, but that if it wants to do this, it has to pay the revenue that's lost because of it. And then we also assume the network has voltage limits of plus or minus 5%, and we set 30-minute trading intervals with 0.05 kilowatt hour peer-to-peer contracts. So the figure on the left in this slide shows the net exported power from the distribution network, and the right-hand figure shows the maximum and minimum voltage levels for 3 different case studies. So the first case study is when we have no peer-to-peer trading and no price spread scale factor. So we're just pricing energy at the forecast DLMPs. We then look at having no peer-to-peer trading, but a price spread scale factor of 1. So we have some level of conservatism. And then finally, we look at the operation with peer-to-peer trading and a price spread scale factor of 1. So the blue line shows the case where we have no price spread scale factor and no peer-to-peer trading. And in this case, we get significant export during the day when we have excess PV. And also we have export at night during certain high price time intervals. Looking at the maximum voltage limits in the network on the right-hand side, we can see that this creates voltage limit violations during the night. And also we can see that during the day, we're operating at the maximum voltage limit. And the DSO in this case has to actually curtail PV generation to prevent voltage limits during the day. Now, with the price spread scale factor introduced, which is the dashed orange line, we see that the voltage limits have been alleviated. However, we can see that during the day, there's less export of energy. And so this kind of means that we're underutilizing the export capacity of the distribution network. And then finally, with the dotted orange line, which shows the peer-to-peer energy trading being reintroduced into this price scale factor 1 case study. So in this case, we get lots of renewable export again during the day. And since prosumers are able to arrange transactions to make use of neighbors' energy storage systems, this still doesn't cause voltage limit violations. All right. So taking a broader view, we can look at what happens with a range of different price spread scale factors, ranging from 0, which is the minimum value, up to 3, which is kind of very large because this is relative to the standard deviation of uncertainty. The figure on the left shows the maximum voltage limit violations. And we can see that for both the case with and without peer-to-peer trading, once you have a price spread scale factor above around 0.5, the magnitude of any voltage limit violations is extremely small. The figure on the right shows the net export of energy over the day with peer-to-peer trading and without. And we can see that initially, as we increase the price spread scale factor, the amount of net exports increases. And this is because the conservatism of the price spread means there's an incentive to use more battery energy storage to shift renewable generation, reducing the need for the DSO to curtail renewable export. However, as we continue to increase the price spread scale factor, the prosumers use their resources in an increasingly conservative way. And so we end up getting greater levels of curtailment beyond a certain point. You can see that peer-to-peer trading helps ameliorate this because although the unidirectional prices are incentivizing conservative operation, peer-to-peer trading enables the prosumers to share their collective energy storage capacity with appropriate transactions. So significant curtailment doesn't occur until we get to a very large price spread scale factor. So finally, the left figure on this slide shows the net utility of the prosumers with and without peer-to-peer trading, and the figure on the right shows the net overall utility, which combines the DSO and the prosumers. On the left, you can see that although prosumers prefer lower price spread scale factors to higher ones, peer-to-peer trading benefits the prosumers for all of the scale factors. And this makes sense because once we're basically allowing prosumers to trade with more participants in the network. On the right, the total utility is increased initially as the price spread scale factor increases, since it reduces overall curtailment. Also, we can see that peer-to-peer trading increases the overall utility over a range of price spread scale factors, since it reduces curtailment and improves the utilization of local resources. So although peer-to-peer trading is often seen in the literature as presenting a trade-off between the value seen by prosumers and the value seen by the system, in this case, we can see that it's actually beneficial from a system perspective to have peer-to-peer trading, as long as we have a suitable price spread scale factor, which is ensuring that peer-to-peer trading doesn't introduce constraint violations. So in this work, we haven't developed a method to optimally set the price spread scale factor. What we can see is that at moderate values, it creates value, but if the value is too low, then there may be constraint violations, or if it's too high, then we get to this overly conservative operation. So in future work, we want to look at how you might learn a desirable price spread scale factor, particularly if you're trying to balance competing policy objectives. So in conclusion, we have a paper on this work, which has more details. More broadly, with Professor Cameron Hepburn at the University of Oxford, I'm co-leading a project on market design for scaling up local clean energy systems. And this project is looking at new local energy market designs, as well as redesigning the system level energy markets in the UK to help integrate and coordinate smart local energy systems. And this is part of a broader initiative called the Energy Revolution Research Consortium, which is supporting several large-scale demonstration projects in the UK. As part of this work, we've released Open, which is an open source Python software platform for integrated modeling, control, and simulation of smart local energy systems. And this is the platform that we've used for this work, as well as some other studies. And it's available online. So if you're interested, you're welcome to check out the GitHub link and see whether it could be also useful for your projects. All right, thanks very much for listening.
Thank you, Thomas. It was a very detailed presentation.